I want to start with something you already know, but I want you to think about it differently than you have before. When a tree grows, the part you see is not most of the tree. The trunk, branches, canopy, everything above ground, that is roughly half of the organism, sometimes less. The other half is below the surface, in the dark. In the soil, spreading outward and downward, a system of roots that can extend as far horizontally as the canopy above, and as deep vertically as the tallest branches reach high. It's not a simple structure. It is a branching network of extraordinary complexity, with major roots the diameter of your arm, extending far from the base, and secondary roots branching from those, and tertiary roots branching from those, and root hairs at the finest tip so small they are invisible to the naked eye, but so numerous that a single mature tree can have hundreds of miles of root length in total. All of this is underground. All of this is invisible unless something reveals it, and most of the time nothing reveals it. The roots do their work in the dark. We walk above them without knowing they are there, and we think the tree is the part we can see. Now I want to ask you to think about what that means at a different scale, not the scale of a tree, a different scale entirely. What if the root system of the largest organisms that ever grew on this planet was so large that what we currently call geological features, the ridges, the canyons, the networks of valleys and channels that cut across the landscape in patterns we attribute to water erosion and tectonic activity? What if some of those patterns are not what we think they are? What if some of what we call drainage networks and fault systems and erosional channels are something else? What if they are the traces, the impressions, the fossilized shadows of root systems so large that they reshape the surface of the earth, the way a very large tree reshapes the soil around its base? I am not telling you this is true. I am asking you to hold the question open and look at what it points toward, because I think what it points toward is interesting. Here is what we know about how roots interact with their environment. Roots do not simply grow through soil passively, they actively reshape it. The pressure exerted by a growing root tip is considerable, enough to crack concrete, to split rock, to lift pavement, to deform the surfaces around them, in ways that are permanent and large-scale relative to the size of the root doing the work. A root the diameter of your wrist, growing along a crack in rock, will over decades widen that crack, force the rock faces apart, alter the drainage patterns of the surface above it, and ultimately, when the tree dies and the root decays, leave behind a channel, a void, a linear depression in the landscape that will persist long after any trace of the root itself has disappeared. Now scale that process up, not to the scale of a tree you can see, to the scale of something whose trunk base might be measured in miles. What does the root system of an organism that large do to the landscape it grows in? What channels does it carve? What ridges does it push up between root paths? What networks of linear features does it leave behind? When it dies and the root material is gone, but the impressions it made in the rock remain? I keep asking this question when I look at certain landscapes from above. I keep asking it when I look at aerial photographs of canyon systems and valley networks and the branching patterns that rivers follow across plains, because the branching patterns that roots make and the branching patterns that rivers make are not always easy to distinguish from above. And I think that confusion, that visual overlap between the two kinds of branching, is worth examining carefully. I want to spend some time on what we know about root depth, because I think the depth question is where this gets most interesting. The deepest confirmed root system ever documented belongs to a wild fig tree in Echo Caves in South Africa, whose roots were found at a depth of approximately 400 feet below the surface. 400 feet. That is not the estimated maximum depth for roots of that species. That is the confirmed depth at which roots were physically observed, because a cave system happened to provide access to that depth. The confirmed depth is not the maximum possible depth. It is the maximum depth at which human observation was possible. If no cave had been there, those roots would be unknown. Their existence would be inferred from indirect evidence, from patterns of moisture in the rock at that depth, from anomalies in the mineral chemistry of the material, from the slight displacement of rock layers that a root growing through them might produce over decades or centuries, and most of that indirect evidence would not be noticed, because the question of whether roots might reach that depth would not be asked, because we would have no direct observation. We would look at the cave walls and see geology, and the root traces would be geology to us, because we would have no frame of reference to recognize them as anything else. Now I want to go further. I want to ask about the chemistry. When a root system decays, when the organic material that formed the root breaks down and is processed by soil organisms and eventually disappears from the geological record, what is left behind? What chemical signature does a large root leave in the rock after millions of years? The answer, as far as current science can tell, is a complex mixture of things: carbon compounds in altered forms, iron and manganese deposits, because roots concentrate these minerals from the soil as they grow, silica in patterns consistent with the cellular structure of the original root tissue, phosphorus and potassium anomalies, and most interestingly, distinctive patterns of chemical alteration in the surrounding rock. What geologists call rhizoliths when they are small enough to be recognized as root traces, but which at larger scales might not be recognized as biological at all. Rhizoliths are calcified root traces, the mineral replacement of root channels, found in many sedimentary rock sequences. They are well documented. Geologists use them as indicators of past soil conditions, past vegetation, past climates. What interests me is not the small ones. What interests me is the question of what a rhizolith looks like when the root that produced it was not centimeters in diameter, but meters or tens of meters or something larger still. At what point does a calcified root trace stop being recognized as a root trace and start being classified as a geological structure with no biological explanation? I do not think anyone has asked that question at scale. I think the answer might change what we see in the landscape around us. Let me try to make this concrete with a specific type of feature. There are formations on several continents that geologists classify as dikes, intrusions of rock that cut across the surrounding geological layers at angles that suggest they were forced through from below, filling cracks or channels that already existed in the surrounding rock. Dikes are real geological features. Magma does intrude through cracks. The geology is not wrong about this, but I keep asking about the channels themselves, the pre-existing cracks or voids that the magma or mineral-rich fluid filled. Where did those channels come from? What created the void that was then filled by the intruding material? In many cases, the answer is fractures produced by tectonic stress, which is a real process. But in some cases, the geometry of the channel, its branching pattern, its tapering width, is not what you would expect from a tectonic fracture. It is what you would expect from a biological channel, from a root path, from the space left behind after a large root decayed. I am not saying every dike is a former root trace. I am asking whether any of them are, and I am asking whether anyone has looked at the geometry of dike systems with that question in mind. The branching question is the one I keep returning to, because branching is one of the most distinctive signatures of biological systems. Physics produces branching too. Rivers branch, lightning branches, cracks in cooling rock branch. But biological branching has specific characteristics that distinguish it from physical branching in most cases. Biological branching tends to be self-similar across scales, the same branching pattern repeating at larger and smaller scales. Biological branching tends to optimize for coverage, for reaching the maximum volume of the surrounding medium with minimum material investment. Biological branching tends to show a specific mathematical relationship between the diameter of a parent branch and the diameters of the daughter branches. When I look at river networks from above, from the kind of altitude that allows you to see the whole drainage basin at once, I see branching that sometimes has these characteristics and sometimes does not. The cases where it does not, where the branching is too regular, too self-similar, too geometrically precise for a physical erosion process, are the cases I find most interesting. I am not saying those cases are former root systems. I am saying they deserve a closer look than they typically receive. Now I want to talk about something that is documented and real and that I think opens the question wider: the mycorrhizal network. This is not a hypothesis. This is well-established biology. Most trees on Earth form a symbiotic relationship with fungi in which the fungal network extends the effective reach of the root system. The fungal threads, called hyphae, are so fine that they can penetrate spaces in the soil that roots cannot reach. They carry water and nutrients from far beyond the tree's root zone back to the tree, and in exchange the tree provides the fungus with sugars produced by photosynthesis. The result is a network that is not purely the tree and not purely the fungus, but something between them, a composite organism of enormous spatial extent. In a mature forest, the mycorrhizal networks of individual trees connect to each other, forming a continuous network that links trees across the entire forest. Carbon and water and chemical signals move through this network from tree to tree. A large tree in the center of a network can subsidize a smaller tree at its edge that is not receiving enough light. The network is a sharing and communication system for the forest as a whole. Scientists who study it sometimes call it the wood wide web. And what I want to ask is this: what does the wood wide web of a forest of organisms, at the scale I have been describing, look like? What does the mycorrhizal network of trees whose trunks are miles wide and whose root systems extend for tens or hundreds of miles in every direction look like as a geological feature? How deep does it go? How dense is it? And what does it leave behind when the organisms it served are gone? I think the answer to that last question might be something we are already seeing in the geological record and not recognizing for what it is. The coal measures of the Carboniferous period, the compressed plant material that we burn for electricity, are not uniformly distributed. They occur in seams, in layers, in networks of connected deposits that geologists map and mine. The geometry of those networks is usually explained in terms of the ancient swamp environments in which the organic material was deposited. The swamps were here and there and in between, and the coal reflects that distribution. But I want to ask whether the distribution of coal deposits also reflects something else, whether the spatial organization of the largest coal fields, their branching and spreading patterns, carries the signature of the biological network. Whether the coal seams are, among other things, the fossilized network, the mineralized traces of root and fungal systems. I cannot answer that question. I do not have the tools to answer it, but I think it is a scable, and I think it has not been asked in that form. Let me talk about something closer to the surface. Something you might be able to go and look at. There are locations on several continents where very large organic structures have been preserved, in a form that is recognizable as biological in origin, but that is not classified as plant material in the way that petrified wood is. These are structures of silicified or calcified material that show what appears to be cellular geometry at a microscopic level, but that occur at scales and in contexts where biological origin is not the standard explanation. I want to be careful here because I do not want to overstate what I know. I am not pointing to specific formations and claiming I can prove they are biological. I am noting that there is a category of geological material, broadly distributed, that shows characteristics consistent with biological origin, and that has not been systematically examined with biological origin as a hypothesis because the scale is outside the range where biology is typically expected, that gap between the characteristics. And the hypothesis is what I think needs to close. And closing it requires applying analytical techniques at scales where they have not been applied before. Here is the thing about petrified wood that I keep coming back to. We find it everywhere, literally everywhere. The petrified forest in Arizona covers 220 square miles of landscape where the surface is carpeted with sections of fossilized wood. But the petrified forest is not unique. There are petrified forests on every continent. In Antarctica, where the climate today could not support any significant tree growth, there are petrified forests from the Triassic and Cretaceous periods. In the Sahara Desert, in one of the driest places on Earth, there are petrified forests. In Patagonia, in India, in Canada, in Siberia, wherever you find sedimentary rock sequences from the right geological periods, you are likely to find petrified wood somewhere in or near them, and the sizes of the specimens are not modest. The largest individual specimens in Arizona have trunk diameters of several feet. The specimens in the Namibian petrified forest include trunks that are several feet in diameter and retain their three-dimensional form in extraordinary detail. These were large organisms. They were large enough that their trunks have survived hundreds of millions of years of geological processing and are still recognizable as the trunks of very large trees. What I want to ask is about the rest of those trees, the parts that are not the trunk, the roots. The root systems that extended from these trunks into the surrounding soil. Where are they? Not the small root tips. The major roots, the primary root structures, the arms of the root system that would have extended perhaps as far horizontally as the tree was tall, anchoring an organism whose trunk was 3 or 4 feet in diameter. Those roots would have been substantial. They would have penetrated deep into the surrounding rock. And when the tree died and the trunk was preserved and the root system was not preserved in the same way, the void left by the roots would have been filled by surrounding material, or the roots themselves might have mineralized differently than the trunk, being thinner and more porous, and more intimately connected to the surrounding soil chemistry. What does a mineralized root system look like when the root was part of a tree whose petrified trunk is several feet in diameter? I think it looks like something we already have a name for. I think it looks like what we currently call geological structure. I think it looks like the matrix of the rock formation that surrounds the petrified trunk, and I think we have been looking at it for 2 centuries and calling it geology because we were looking at the trunk and not looking at what the trunk was connected to. There is a word I want to introduce here, rhizolith. I mentioned it earlier, but I want to spend more time on it now because I think it is the key to understanding what I am pointing at. Rhizoliths are the mineral traces of ancient roots preserved in sedimentary rock. They form when a root growing through sediment is replaced by mineral material, either while the plant is still alive through a process of gradual mineralization, or after the plant dies and the root channel is filled by sediment or mineral precipitation. The result is a structure in the rock that preserves the shape of the original root. Rhizoliths are common. Geologists find them in many sedimentary sequences and use them as indicators of past soil conditions and vegetation. The ones that are typically described and studied are small, centimeters in diameter, sometimes a few inches, occasionally larger, but the principle of rhizolith formation, the mineral replacement of root channels, applies to any root regardless of size. A root 10 feet in diameter, or 100 feet in diameter, or larger still, would produce a rhizolith 10 feet or 100 feet or more in diameter. It would produce a structure in the rock that is the exact shape and geometry of the original root, mineralized and preserved, but so large that it would not be recognized as a root trace by anyone who was not specifically looking for a root trace at that scale. It would be recognized as a geological feature. A ridge, a dike, a channel fill, a structural element in the surrounding rock whose origin is explained in terms of the local geological history without any reference to the biological possibility, because nobody is looking for rhizoliths at that scale. The concept exists for centimeter scale features. Nobody has extended it to kilometer scale features and asked what the landscape would look like if it were full of them. I want to close this by going back to the beginning, to the thing I asked you to think about differently at the start. The part of the tree you cannot see, the half that is underground, doing its work in the dark, reshaping the rock it grows through, extending the organism's reach far beyond what the visible canopy would suggest, connecting to other organisms through networks of fungal threads, altering the chemistry and structure of everything it touches. For most of the history of botany and geology, the root system was the forgotten half of the plant. The science of roots is younger than the science of stems and leaves. The ecology of root interactions is younger still. The mycorrhizal network was not described in scientific literature until the late 19th century and was not fully appreciated as a forest-scale phenomenon until much more recently. We are still learning what roots do. We are still learning how far they reach and how deep they go and what they leave behind. And that learning is happening at the scale of the trees we can see and study, the trees of the present world, trees that are large by our standards but modest by the standards I have been gesturing toward. Throughout this video, the question of what the root systems of organisms at a different scale, in a different atmosphere, in a different geological period, might have looked like and left behind is a question we have not begun to ask seriously. Not because it is unanswerable, because it is large, because it requires holding a frame of reference that most of us have never been given the tools to hold, because it requires looking at the landscape as something that might be full of biology rather than something that is simply geology with some biology sitting on top of it. I think the landscape might be full of biology. I think the roots might be everywhere. I think we have been walking on them our entire lives and calling them rock. And I think the question of whether I am right is one of the most interesting questions I have encountered in a long time, not because I know the answer, but because I do not, and because the not knowing points somewhere that I find it very hard to look away from. There is a specific phenomenon I want to examine now that I think brings the root question into sharper focus. It is called an anchor root. In very large trees, the root system is not uniform. There are fine feeding roots that spread widely through the upper soil, absorbing water and nutrients across a broad area, and there are anchor roots, sometimes called sinker roots, that grow primarily downward, deeply, providing stability rather than nutrition. In a very large tree, the anchor roots can be enormous. A coast redwood with a trunk 40 feet in circumference has anchor roots that penetrate several feet in diameter at their origin and extend straight down before spreading laterally at depth. These are not the fine hair-like feeding roots. These are structural members, load-bearing elements of the organism, performing the same function as the pilings of a bridge, transferring the lateral forces of wind and weight through the soil and into the rock below. Now ask what an anchor root of an organism at the scale I have been describing would look like, not a 40-foot circumference tree, something much larger, an organism whose base is measured not in feet but in miles, the anchor roots of such. An organism would not be measured in inches. They would be measured in something else entirely, and they would penetrate not through soil but through rock.
Not because rock is their preferred medium, but because an organism large enough and old enough would eventually grow down past any soil layer and into the bedrock beneath, and would then continue, because roots do not stop when they encounter harder material. They find the cracks, they follow the water, they go wherever the chemistry and the pressure differential lead them, and they reshape whatever they pass through. What would such a root look like when mineralized? What would a vertical column of organic material, perhaps hundreds of feet in diameter, that once extended from the base of an organism into the rock beneath it, look like after hundreds of millions of years of chemical processing? It would look like a vertical intrusion of material distinct from the surrounding rock. It would look like something that cut through the geological layers rather than conforming to them, because the root grew through pre-existing layers rather than being deposited as part of them. It would look, in short, like what geologists call a pipe structure, or a vertical dike, or a chimney, or any of several other names for vertical geological features whose origin is attributed to various processes of igneous intrusion or fluid movement through rock. I am not saying every pipe structure is a former root. I am asking whether some of them might be. And I am asking whether the analytical tools that could distinguish between a mineralized biological channel and a geological intrusion have been applied to the full range of vertical structures we find in the rock record, at all scales, with the biological possibility as a genuine hypothesis rather than as something that is dismissed. Before the analysis begins, the water question is central to all of this. Roots follow water. Every root system is, among other things, a water-finding and water-transporting network. The root tips extend toward moisture gradients. The root channels carry water upward, from depth toward the surface, against gravity, driven by the transpiration of water vapor from the leaves above, which creates a continuous tension in the water column that pulls water upward through the entire organism. In a very large tree, this hydraulic system is extraordinary. The tallest living trees are pushing against the physical limit of how high a continuous water column can be maintained by transpiration alone. The taller the tree, the more difficult it becomes to pull water from the roots to the leaves, because the height of the water column creates more resistance. This is one reason that many scientists believe there are physical limits on tree height, and that those limits are somewhere in the range of the tallest trees currently living. But those limits are calculated for the current atmosphere, the current oxygen and carbon dioxide concentrations, the current atmospheric pressure profile. In a different atmosphere, in a denser atmosphere with different pressure at the surface, the hydraulic limits would be different. The maximum possible height of a water column, maintained by transpiration, would be different, and the depth to which roots would need to reach to supply the water demand of an organism of very great height would also be different. The root system and the canopy are part of the same hydraulic machine. If the canopy can reach higher, the roots must reach deeper. And if the roots reach deeper, the geological traces they leave behind are deeper too, and more permanent, because deep rock is harder and more resistant to erosion, and structures formed in deep rock are more likely to survive over geological time than structures formed in shallow soil. I want to say something about the fungi again, because I think the fungal question is the one that opens the most space for asking new things. We know that mycorrhizal fungi extend the effective reach of root systems by orders of magnitude. We know that in a mature forest the fungal networks connect individual trees into a continuous biological network. What we do not know, what I do not think anyone has asked in a systematic way, is how deep the fungal networks go. We know that mycorrhizal associations occur in the root zone, which in most trees is concentrated in the upper layers of soil, but some fungi are not limited to the root zone. Some fungi penetrate much deeper, following water tables and mineral gradients into rock. The fungi that colonize caves, that grow on the walls of deep mines, that have been found in boreholes at depths of miles below the surface, are demonstrating that fungal life is not confined to the soil layer. It can go wherever there is chemical energy to be extracted and wherever the physical conditions permit survival. Now ask what the fungal network of a forest of very large organisms would look like. Not a network confined to the upper soil layer, a network that followed the root systems of those organisms wherever they went, which, if the organisms were large and old and growing in a deep atmosphere world, might mean a network extending hundreds of feet or more below the surface. A network threading through the rock, altering its chemistry, processing minerals, leaving behind its own traces alongside the traces of the roots it was associated with. The biological signal in the rock at depth would not just be the root channels. It would be the entire altered chemistry of the rock through which the fungal network passed, and that altered chemistry, at depth, far from the surface where it might be recognized as biological, would be classified as geological. As the natural result of fluid movement through rock, as the ordinary chemistry of diagenesis and mineralization, because nobody is looking for fungi at that depth. Nobody is asking whether the altered rock chemistry in a deep borehole might carry the signature of an ancient biological network rather than a purely geological process. Here is what I find most arresting about all of this. We live on a planet whose surface and near-surface geology is the product of billions of years of geological processes and hundreds of millions of years of biological activity. The two are not separable. The chemistry of the rocks near the surface has been profoundly altered by life. The oxygen in the atmosphere, which affects the oxidation state of surface minerals everywhere, came from photosynthetic organisms. The carbon in limestone and chalk and other carbonate rocks came largely from the shells and skeletons of biological organisms. The coal and oil in the ground are transformed biological material. We know all of this. We accept it. We teach it in geology courses alongside the purely physical processes of erosion and deposition and volcanism. But I think the full extent of biological influence on the geological record is something we have underestimated, systematically, because we have been studying it at the scale of the organisms we know, rather than asking about the scale of organisms we have not yet recognized. And I think the root systems of very large trees, the anchor roots, the mycorrhizal networks, the rhizoliths at scales we have not yet considered, are part of that underestimated biological signal. They are in the rock, they are in the landscape, and they are waiting for someone to ask the right question about them.